graining on that wood, graining on that wood. I'm swerving on that, swerving on that big body, been serving all this, surfing all of this.
The structure that we are going to analyze throughout this video will be a surfboard. A surfboard can be seen as a sandwich structure. A sandwich structure consists of two thin, stiff layers separated by a thick, lightweight core. The core is usually made out of balsa wood, honeycomb, or foam. The laminate layer above and below the core is usually made from flax mat and epoxy resin. The figure on the screen shows the components of the sandwich structure. It shows the top layer is in compression, the bottom layer is in tension, and the core consists of shear forces. A surfboard must be able to withstand wave forces, and so they must be flexible, stiff, lightweight, have high tensile strength, and they also should be able to bend. It also must allow for balance between the weight of the surfer, the buoyant forces, and the friction forces. Structural analysis of a surfboard is intended to determine whether or not the board will be able to endure multiple loads applied. Significant loads are considered when surfing. To start off with, face sheet utilizes most of the load to prevent bending, whereas the core resists shear forces and compression. Furthermore, laminate plays a role to protect the core from impact loads and helps disperse points over a larger area. The first load that we will consider in the analysis is compression. The board is obligated to withstand the load of the person compressing it past its elastic range. The resistance that leads to compression arises mainly from the core, which has the largest potential for substantial deflection. Although the interaction between the laminate and the board would indicate that the load applied to the laminate will be spread over a larger area when applied to the core. In addition, the laminate offers a certain amount of flexural resistance which will assist the core resisting compression. The image shows the compression forces the surfboard is experiencing while a right-footed pro surfer is surfing on it. The green and blue areas on the surfboard are compression forces, whilst the dark blue is the maximum pressure the surfboard can handle. The yellow area is not affected. The picture shows the forces on a surfboard when it is hit with a wave. The lip of the wave presses down on the deck of the surfboard with a lot of force. The water under the surfboard prevents it from moving down under the force of the wave. The force on the top of the surfboard causes the top of the deck to compress, carrying compression forces, and the bottom of the board to stretch, carrying tension forces. Comparing this value with the compressive yield strength of 1.13 megapascals gives us a safety factor of 13. Considering the other factors mentioned above that will aid in resisting compression, it becomes clear that the compression of the board will not be a problem. This will also allow for more leeway in instances where impact loads are applied. There must be limited bending in the surfboard in order to uphold proper lamination and avoid failure. Most of the load in the bending must be absorbed by the laminate as the core is much weaker. To simplify the board structure, let's consider a sandwich beam and stresses which are applied to the laminate and core. Working out bending, we must consider, first off, maximum stresses which will occur when the user is standing because the loads are more localized, causing larger bending moments. Secondly, force exerted on the board by the water must be considered. The force is an evenly distributed load over the bottom of the board. Lastly, there are occasions where the board will be partially in contact with the water. The diagram shows a concentrated load at the center of the beam, supported by a uniformly distributed load across the bottom. Because the curvature of the board is minimal and the load is concentrated in the center, the board can be approximated as a regular prism or a simple beam. The design strength of the materials will be based on the maximum bending moment in the beam and an appropriate safety factor. Therefore, we need to determine the maximum bending moment in the beam. In order to perform the analysis more easily, we will flip the figure upside down and only consider one half of the beam. The internal moment M in the beam caused by W, which is the UDL, can be calculated using the sum of the moments around point A. Since the board is in static equilibrium with no rotational movement, the sum of the moment about A equals 0. In conclusion, the surfboard can be characterized as a sandwich structure and be considered as a simple beam, having similar properties as a simple beam in terms of compression, tension, and bending moments.